All right, and we're going. Go ahead, Alex.
Hi, everybody. Welcome back to the Astro Imaging channel. This is Alex, and I am wearing my RTMC t-shirt because it is, after all, Memorial Day weekend. And even if the RTMC itself has ended, I can still be here. Let me see. I've got it. Hang on for a second. Okay. First thing I'd like to do is switch back over here and share my desktop with y'all, as I do every time. There we go, present now, it's called over in this program. One of the problems with having so many different um, programs that we're working with this now during this time is that there are different ways to do each of these things. They all do the same thing, but there are different ways to get them to do it, and I lose track of which one I'm doing it in. My Zoom meeting is really cool. You know how you can put the background in? So I went over to Google and I did an image search for hoarder house. And so I've got a hoarder's house, you know, with all the junk and everything piled up. That's my background in my Zoom meetings. But at any rate, we should be sharing the channel now, or the desktop, are we? Yes, we are. I wanted to take you over to our calendar. And today is May 24th. Bob Zellem's going to be here, and he's going to be explaining exoplanet search with amateur equipment. I've seen this presentation before, and it's really pretty exciting. He tells us a lot about exoplanets and how we found out about them and what they mean and some things like that. But he's also going to tell us how we, as amateur astronomers with our pretty picture type stuff, can contribute to finding exoplanets. So that's going to be cool. Bob Traub is going to be coming in next week, and he's going to be telling us about comet processing with SWAN coming in to the picture. That's going to be pretty cool to see that. Richard Wright's coming up, and then as you can see, we've got a whole lot of other people all ready to come in and visit with us. And after July 5th, though, we don't have anybody scheduled. So I would encourage everybody to go to their contacts and give us your name and tell us that you'd like to help present something. If you've done something in astronomy, astroimaging, and you would like to share it with us, and it can be at the beginner level, at the advanced level, whatever it is you'd like, send us something, and we'd like to hear from you. This in general is the YouTube screen, and I hope you're all commenting on things over here on the side. Yeah, usually you guys are pretty much into telling us what's going to be happening with, you know, like no clear weather. Yeah, I had a beautiful night last night out at GMARS, and would be having another beautiful night out there tonight, except that I'm here with you today. So, there's also a couple of other buttons down here. You can see the subscribe button right down here. I'm circling it right here. We need some more subscribers. If you're a regular member, you're coming on a regular basis, hit that button and subscribe. You do get to find out where we're coming from each week, and that's cool. And we're up to 8.78K subscriptions right now. We really want to get to about 10,000. We'd like to do that. So put in everything you'd like to talk about over here in the column with the comments, and you can even send us some money someplace around in here, and you know, we'd really appreciate that. Okay, tonight's presenter is going to be Bob Zellem, and I shall turn over the screen to Bob. Bob, you go ahead and take it over from now on, okay?
All right, thank you. Let me flip this on.
Oh, I gotta stop sharing. Okay.
Okay, let me know if you can see my first slide.
Yeah, I see it.
Great. So everyone, thank you so much for having me. Hope everyone's having a nice, hopefully long weekend, staying safe. My name is Rob. I'm a planetary astronomer at NASA's Jet Propulsion Laboratory, and my specialty is exoplanets. And what I really want to do is I want to find life in the galaxy. You should all be forewarned. I'm a giant nerd. Here I am, little mini Rob, with my hero, random NASA astronaut at Kennedy Space Center. I've loved astronomy, I've loved NASA, I've loved science, and truly I am really, really lucky that I get to be part of my dream job right now, which is working at NASA's Jet Propulsion Laboratory in Pasadena, California. So lots of people ask me, Rob, you love astronomy, you love science, why did you never become an astronaut? And the reason is because I am very much afraid of heights, okay? So I've decided to become the next best thing, and I am an exoplanet astronomer. So the long story short, Rob's a giant nerd. I might talk really quickly because I really love this subject. Please feel free to interrupt with lots of questions. We have lots of great moderators out there. We'll be reading your questions on YouTube, and they are more than welcome to interrupt if they feel so, and happy to take questions as I go, or also wait until the very end. So I'm not an astronaut, afraid of heights. I'm an exoplanet astronomer. So let's unpack what that means. So exoplanet. That is short for extrasolar planets. Astronomers were kind of lazy because, that's too many words. That's too many letters, guys. So extrasolar planet becomes exoplanet. Well, extrasolar means beyond the solar system, and planet, hopefully you all know what the definition of that is. Planet equals a planet. Great. So an exoplanet is any planet outside of our solar system. It's not necessarily any planet that's orbiting another star, because there actually are some free-floating planets out there in the galaxy, which is pretty cool. And then I'm an astronomer, and you probably all know what that means. That is someone that stares at the sky, or more likely their computer, for way too long. So I'm very happy to be here with all of you. Thank you so much again for having me. So at NASA's Jet Propulsion Laboratory, what I'm working on is answering this ultimate question. Are we alone in the universe? And to do that, I'm really lucky in the sense that I get to work on a lot of cool missions, instruments, telescopes that are observing exoplanets, our planets outside of our solar system. And ultimately, I want to be able to answer this question. Are we alone in the universe? Because I'm also a giant Star Wars fan. I want to ride the Millennium Falcon, but in order to ride the Millennium Falcon, I gotta find it first, right? So that's why I want to answer this ultimate question, are we alone in the universe? Before we look at where we currently are and where we're going, it's always important to look at where we've come from. Also, I'm married to a historian, and she's literally right outside that door. And if I don't present this slide, she'll bust down the door and cancel this telecom. So let's get through this slide. So a little bit of history. Exoplanets is actually one of the youngest fields in astronomy. It started roughly in the mid-90s. And despite this relatively young field, the idea of exoplanets and the idea of life is actually nothing new. For example, Giordano Bruno, that's that Emperor Palpatine looking like guy on the right side of your screen. He was actually a 16th century philosopher who postulated the existence of planets outside of our own solar system. And Isaac Newton, he's the guy that founded Fig Newtons, right? Well, in his book where he described the theory of gravity, Principia, he also said, and if the fixed stars are the centers of similar systems, they will all be constructed to a similar design. In other words, we have 8 planets, 8 because Pluto's not a planet, guys. Come on, go with it. So there's only 8 planets orbiting around our own sun. So if you were to go into tonight's night sky and look up at all the stars over your head, it stands to reason that there's also planets orbiting around those stars. And now today we know that these 2 dead guys are absolutely correct. We now know of over 4,000 exoplanets because our technology has gotten better, because we know where to look, when to look, how to look, what sort of camera to use, what sort of telescope to use. And due to these advances of technology, we've been able to discover more and more exoplanets. And I'll talk a little bit later about some NASA missions that have enabled these broad discoveries, but ultimately we now know today that for every star that's in the sky, there's at least one exoplanet. So in other words, there is as many planets as there are stars in the sky. So planets are everywhere, and perhaps if planets are everywhere, maybe life is also everywhere. So how do we find life? How do we find aliens? Well, it's a simple three-step method. First, you have to find an exoplanet. Then you have to figure out if that planet can support life or not. Then you actually have to find the life on that planet. So let's look at the various methods for looking at an exoplanet, for finding an exoplanet. And there's actually a bunch of different ways we can do this. But I'll be focusing tonight on these three, because the radial velocity and the transit method are the two methods that we know arguably the most about exoplanets today. The direct imaging method, I'm just got to talk about because it's really super cool. And then the other methods are also very interesting in their own right, and hopefully you'll have some more speakers talking about these other three methods again in the future. So let's first look at the radial velocity method. So as you might know, light behaves like a particle and also behaves like a wave, much like sound does. So if you're ever walking down the street and you hear like a big car go by or an ambulance or a race car, you'll notice that as the car comes towards you, the pitch and sound increases. And that's because the waves are compressed as that car comes towards you. So it'll get higher in pitch. And then when the car drives away from you, those sound waves are stretched out and it becomes lower in pitch. And that's called the Doppler shift. And light does the same thing. When light's coming towards you, the wavelength is compressed and it becomes blue shifted. And then when light is coming away from you, those light waves are drawn out and it becomes red shifted. So what we can do is we can actually take advantage of this Doppler effect and actually use it to discover planets orbiting around other stars. So on the right is an image, a GIF of an exoplanet orbiting around a star. And you'll notice that that star is sort of tugging that exoplanet, much like the sun tugs our own planets and causes our own planets to orbit around our own sun. But that exoplanet is also inducing a gravitational tug on the host star itself. So the host star is actually wobbling back and forth. And if we measure the light coming from that star, we can actually observe that wobble. And we can infer that a planet was orbiting around that star. Now, this is really important because this allows us to actually measure the mass of that exoplanet. The bigger the wobble, the more massive the planet. The smaller the wobble, the smaller the planet. But it's very important because it allows us to weigh effectively these exoplanets. Advantages, it gives us the mass of the planet. However, some disadvantages is that we're biased towards big planets because the bigger the planet, the bigger the wobble. And the faster that that planet orbits around its star, the faster the period of that wobble occurs. Also, if you want to look for Earth-sized planets, we need to use large telescopes. So for example, the Keck 10-meter telescopes in Mauna Kea, is that photo in the top right, those are needed to get to the precision necessary to find small Earth-like planets. So that's the radial velocity method. Now let's move on to the transit method. Now the transit method, this measures the brightness as a planet passes in front of a star, and effectively that planet will cast a shadow on the Earth's surface. So this animation, we have a star, a planet passes in front of the star, and the planet's disk actually blocks out some of the star's light. So relative to Earth, we see that star, and that star's brightness actually diminishes a little bit. And for a Jupiter-sized planet that's orbiting around a sun-like star, that dip in brightness is at best just 1%. So again, we have this planet. It passes in front of the sun, or the star, and it blocks out the star's light, causing the star to get a little bit dimmer. But this is very important because the amount of light that's blocked out by the planet is exactly proportional to the area of the planet to the star. So you can actually measure the size of the planet relative to the host star. And as I'll talk about a little bit later, this method also allows us to study a planet's atmosphere. Now, the transit method is very near and dear to my heart because not only have we used it to discover 3,000 out of the 4,000 currently known exoplanets, this is also the method that I specialized in as a graduate student. So I use the transit method, both from space and the ground, to look at the atmospheres of exoplanets, to characterize their atmospheres, to figure out what the composition of these planets are, if there's water, if there's methane, if there's carbon dioxide, to see how the temperature gradient varied with height. So the transit method is actually very, very powerful because it allows us to determine the planet's size. It actually can be relatively cheap in the sense that I actually saw on Reddit a few years ago, someone took a little DSLR camera and put it on a very simple tracker, and just from the digital camera alone was able to observe the transit of an exoplanet. Also, you can use small telescopes to observe the transits of exoplanets. I'll come back to that in a second. However, just like with the radial velocity method, there are some disadvantages. So for example, you're going to be biased towards large planets. The bigger the planet, the bigger the dip in the brightness of that host star. So we're going to be biased towards finding bigger planets because it's simply a bigger signal. Also, you could have false detections like stellar activity. And also, you need that perfect edge-on view to see a transit. Because if a planet's orbiting in this plane, the planet will not pass in front of its host star and block out its star's light. So earlier, I alluded to lots of exoplanets being discovered in the last few years. And one of those NASA missions that allowed us to really get a better statistical understanding of exoplanets is NASA's Kepler and K2 mission. So Kepler is a satellite that was launched in 2009. It was a NASA planet hunter, and Kepler looked at that very small field of view, roughly the size of the full moon, towards Cygnus 1. And in that small field of view, Kepler discovered over 2,000 exoplanets and potentially another 4,500 as well. So if we take that small field of view and extrapolate the thousands of exoplanets that Kepler found in that small part of the sky to the entire sky, it is thanks to NASA's Kepler that we now know that planets are very numerous. There are at least as many planets as there are stars in the sky. And when there's planets, there also might be life. So Kepler unfortunately died a few years back because it lost control of its reaction wheels, but fret not, we actually have a new mission that was launched about a year or two ago called NASA's TESS mission. So while Kepler looked at one small part of the sky, TESS is now doing a full sky survey. And this mission is projected to discover up to an additional 10,000 new transiting exoplanets. So currently we know 4,000. TESS might give us an additional 10,000. And this is great because TESS will give us many different targets that we can look at with future NASA missions and current NASA missions. For example, Hubble today has been observing tens of transiting exoplanets to look at their atmospheres. James Webb, that's the successor to Hubble. It's an absolutely giant telescope. That mirror in gold is about 6 meters or about 18 to 20 feet. The purple part on the bottom is actually the size of a full tennis court. That's its sun shield. And James Webb is projected to look at tens to hundreds of exoplanets. The European Space Agency in 2028 will be observing hundreds to 1,000 exoplanets. And TESS will be providing each of these missions as we go along hundreds, if not thousands of targets that we can look at, that we can characterize, that we can understand their atmospheric content to determine if life could exist on an exoplanet. However, if I want to observe a transit, I have to know exactly when that transit occurs. So right here, one second. This is where I think my transit will occur. So for example, if I write my Hubble Space Telescope, I say I want to observe this transit that occurs at this time. Or my James Webb Space Telescope proposal to observe this transit that occurs at this time. But if there's some uncertainties in my transit, and my transit actually occurs an hour or even just minutes earlier, I run the risk of missing, partially clipping, or completely missing that transit. So for example, if a transit has an uncertainty of about 5 minutes, that's an extra 5 minutes that I need to build into my observing campaign to make sure I observe that transit. So again, 5 minutes doesn't sound like a lot, but time on instruments like Hubble, like James Webb, there are only those two space telescopes that are able to characterize in detail exoplanets and do a lot of interesting science in addition to exoplanet science. So we want to use these precious resources as effectively and efficiently as possible. So we want to cut out the overhead as much as possible. Ariel, for example, will be looking at potentially 1,000 exoplanets. And now when I multiply a 5-minute uncertainty times 1,000, that starts accumulating into a lot of time that Ariel will be wasting trying to observe these transits. But the great thing is this is exactly where amateur astronomers can step in and help out NASA missions. So on the right, I'm showing an example transit of an exoplanet. It's a hot Jupiter, a large Jupiter-like object orbiting very close to its host star called HAPP-32b. And this data set on the right was actually taken by a 6-inch robotic telescope in Tucson, Arizona. The tracking wasn't the best. It actually moved over 300 pixels on the focal plane. And despite this being a relatively small telescope, despite the tracking not being the best, we're getting an absolutely beautiful light curve on the right-hand side of the screen. And this uncertainty that we're able to measure in the mid-transit time and the transit depth is absolutely exquisite. And actually, we were able to publish this data in a paper that I was able to publish within the last month in an academic journal. So small telescopes absolutely have the power to do very important science, very important transit measurements of exoplanets. So this data return and getting lots of people such as yourselves saying they want to be involved in helping out and aiding NASA missions is what inspired me to launch a citizen science project called Exoplanet Watch. And this is a campaign aimed at citizen scientists to routinely observe high priority transiting exoplanets. So all of you could go out tonight or the next few nights whenever it's clear and dark and good seeing. You can observe transiting exoplanets and reduce your own data and upload your results to our database. And in doing so, you will contribute to using large NASA missions like Hubble, like James Webb, like ESA missions, such as Ariel, even next generation missions from NASA, such as an Astro 2020 mission that might be looking for signs of life. You will directly help out those missions to use them more efficiently. So this data will be immediately public to the entire community. And if you contribute to a paper that's been published, we will request and require that those authors include you as a co-author. Since you're doing all the work, you deserve the credit, right? So we're actually starting beta testing right now, and we'll be likely launching officially in September of 2020. I'll show an additional slide in a second if you want to get involved. But in case you want to look right now, just Google NASA Exoplanet Watch, and there's details on how to get in touch with me. I'll email you back probably on Tuesday morning. So another great thing about this project is we have developed our own data reduction tool called Exotic. This is actually done by my undergraduate student intern, Ethan Blazer. He's an undergrad at University of Virginia. And he actually built this data reduction tool that takes your raw images and completely reduces and models the data to fit it with a model light curve. So this light curve that I showed a little bit earlier, this is actually reduced completely by Exotic. So as long as you go out in the field, You take your images, you take your fit files with like the SkyX or MaximDM or something like that, and then you feed them into Exotic. You can produce in as little as an hour a fully reduced, statistically sound data set. Another cool feature of Exotic is it's actually able to make light curves in real time. So let's say once these restrictions are finally lifted, hopefully very soon, if you're ever hosting a star party, you can actually observe a transiting exoplanet in real time. So normally observing a transit, it's not too interesting. You're observing a host star dim by 1%, and that's hard to see by the eye. But Exotic is capable of reducing the data in real time. So you can actually tell people, look, we're observing a planet outside of our solar system. So we absolutely need any of you that are willing to participate. So we're looking for observers, we're looking for beta testers to observe any exoplanet, any transiting exoplanet at all, and upload your results to the AAVSO exoplanet database. We're very fortunate in that the AAVSO is actually one of our collaborators. Also, for those without telescopes, if you don't have any data, that's not an issue at all. Let me know, and we'll be able to hook you up with a bunch of archival data that is absolutely needs to be reduced. We also need you to help out with beta testing our exotic data reduction code. Again, we'll be launching officially probably around September of this year. And if you're interested, you can contact me at that website right there. I'll get back in touch with you probably Tuesday morning, or alternatively, just Google NASA Exoplanet Watch. You can find our website that way. All right, so I'll get off my soapbox now. I've discussed the radial velocity method. I've gone over the transit method. Now let's move on to the direct imaging method. As you probably figured out. Oh, go ahead. Yeah,
before
please.
we go on.
Yes.
We have had some comments and discussions over there. For one, the old Pluto thing. I mean, you probably heard about that, but about whether it's a planet or not. But Guillermo Yanez has a couple of questions, and they're related to the size of the planets in the radial method and then the transit method. How big does a planet have to be in order to be seen, detectable? What do you know about that? What can you tell us about that?
So for the radial velocity method, we need roughly the precision in order to find a Jupiter-sized planet of 1 meter per second. So that's like a brisk walk. In order to find an Earth-sized planet, we need something like on the order of centimeters per second, which is like a very slow walk. So currently, ground-based telescopes can easily find Jupiter and Uranus and Neptune-sized planets and Saturn-sized planets. Earth-sized planets, we're just starting to be able to have the precision to discover and detect those with the radial velocity method. The transit method, we're actually able to observe Earth-sized planets. If you have a 6-inch telescope, you could easily observe a Jupiter-sized planet orbiting around a sun-type star. If you have something a little bit bigger, like a 14 or 16-inch telescope, you might, if you have nice seeing and dark skies, you might be able to observe a Neptune or potentially an Earth-sized planet as well.
Does the detectability depend also on the size of the star that the planet is circling?
Exactly. So a bigger planet, a bigger star, it'll be harder to observe a smaller planet. So that's why astronomers have looked after M-dwarf stars or small stars, roughly 10 to 100 times smaller than our own sun. Because if the star is smaller than the planet, its signal will look comparatively bigger. So a Jupiter-sized planet will be the amount of light that a Jupiter-sized planet blocks out will be much larger around a small star than a big star. If we take an Earth-sized planet and put it around a small M-dwarf star, then its transit depth will be on the order of 1%. So that's how actually some small telescopes, for example, will be able to measure the transits of small Earth-sized planets.
Glenn would like to know if you can distinguish between one big planet and two small planets orbiting the same star.
Yeah, so these two small planets, for example, I'll talk a little bit later, is the TRAPPIST system. This is actually a 7-planet system orbiting around its host star. And since these planets will all have different orbits around their host star, they'll all transit at slightly different times. So you'll see a smaller transit, you'll see multiple of them. And if you observe them many, many times, you can actually pull out that there's actually 2 planets instead of just 1.
Can you comment about why um, why aren't planets always? Elmico wants to ask this. Why aren't planets always in the same orbital plane? I guess is actually he said it better than I'm saying. Um,
Yeah. So it's just happenstance, right? So when you have a giant gas and dust cloud that forms a protos solar system, you have all that gas and dust collapsing at the center to form a star. And you have the rest of that gas and dust that starts to collapse and form a solar system. So pretend that you're like making pizza tonight, right? And you have that ball of dough, and then you flip it up in the air and you rotate and you spin it around. It forms that nice disc, that delicious, delicious pizza disc, right? So
mhm.
that orientation of that disk can be at many different angles. So if I have a planet orbiting around its star in this motion, I will not see a radial velocity and I will not see a transit. But if the orientation happens to be like this, then I will see a radial velocity and I will see a transit.
Okay, Eric, have we got any others over there? I think I got them all.
I have a question, Rob. Let's say you have a telescope with a field of view, say 1 degree by 1 degree. There are a lot of stars in that field of view. With the project that you're talking about, can you look at many stars, or do you have to focus on a small number of stars?
Yeah, so for Exoplanet Watch, what we do is on our website is we identify a high priority target every single night. So we actually pre-identify for our users what sort of targets we want you guys to help us monitor. There's nothing preventing you though from observing any transiting exoplanet at all. In addition, you have a very large field of view such as that. You can use it to monitor multiple stars in your field of view. Exotic, our data reduction tool, what it does is it measures the light from one host star at a time. So there's nothing preventing you from running, for example, Exotic multiple times to observe the light curves of multiple exoplanets. Alternatively, you are more than welcome to use any of your own data reduction tools. Let's say you have your own method you coded up by hand, or if you like AstroImageJ or ExoFast, it doesn't matter. As long as your data is in the final text format that's required by the AVSO, you're good to go.
So you have to look at 1 star at a time with the software that your group has developed.
You can look at multiple stars at once, but the reduction tool we built to save on computational power, to allow it to run on your home laptop, we reduce 1 star at a time. Yes.
Do you have a piece of hardware in the cloud that could reduce your data and perhaps handle a little more?
Yeah, so we actually have a student, a high school student that was very motivated these past few months, and they actually moved Exotic into the cloud. So if you're interested in running Exotic on the Google Colab cloud, you can just send me an email and I can add you to our Slack channel and we can get you in touch on the instructions on how to run that as well.
And I see a question came up. Does the exoplanet have to cross right and equatorial, or can it, be a little higher or lower and still detect?
It can be a little higher or lower as long as it blocks out the light from the host star. Exactly.
Okay, I think we're good.
Cool. All right.
I have a question before we go.
Sure.
The Exotic software, is that going to be a little bit more user-friendly than AstroImageJ?
I hope so. We're doing beta testing right now, so we're always looking for customer feedback. We're trying to make it as user-friendly as possible. You do run it in the terminal, albeit, but by running in the Google Colab, it's pretty user-friendly, as well as running on your own laptop. You can get it running on a Windows, a Mac, or a Linux computer, and For example, it automatically scrapes other websites to get parameters to feed the reduction code. So we tried to really make it as user-friendly as possible.
And Exotic works pretty much like other photometric software, where it compares your brightness with other stars of known brightness, and I assume. Okay.
Yep. So it does multi-object photometry. It picks out the best comp star. It picks out the best annulus. It picks out the best centroiding. It does all that for you. All of the user inputs are up front. So let's say you observe a transiting exoplanet one night and you want to run Exotic. It only requires about 2 to 5 minutes of user input. And then you run it, you go to sleep, you wake up, and you come back to reduce data in a beautiful light curve.
How these planets that you've become familiar with, how often do they, what's a year for one of these planets? How long is it between transits in these things?
So a lot of the planets we're discovering are very close to their host star. So a lot of them orbit around their star once every few days. So one exoplanet that I looked at a lot in graduate school orbited around its star roughly every week or so. There are planets that whip around their star on the order of days, if not hours. So these are all very close in exoplanets, because the closer they are to their star, the more they transit, the more they transit, the more easy it is to discover them.
Thank you. We got everything, Eric. Are we ready to go on?
Yeah, I think we're good.
Okay,
Cool.
Rob, take over.
So direct imaging is the other method I was going to talk about today. And that is exactly what it sounds like. This is exactly taking photographs of exoplanets. So the problem is seeing the planet through the glare of its host star. So if you took a large planet, something that's easier to see, and make it really hot so it emits a lot of light, well, let's stick that around like a sun-like star. The amount of light that that planet would emit is the equivalent of looking for a firefly around a lighthouse and you're over a mile away. Now let's make it a little bit harder. Let's shrink that planet down to the size of an Earth-sized planet. Let's also make it a little bit cooler, something that's habitable, like our own Earth. Let's take the Earth around a sun-like star. How easy would it be able to observe that exoplanet? Well, the answer is it would be very difficult if you're looking for the light from one bioluminescent alga floating around that same lighthouse. So the problem is how do you get rid of the light from your lighthouse or your star? How do you block that light so you can see the light emitted or reflected by that exoplanet? And the answer is a process called direct imaging. So right here is a picture of an exoplanet host star. This is a star that actually has a planet orbiting around it. But since the star is so much brighter than its exoplanet, the host star outshines the light from the planet. So I'm assuming a bunch of you probably, hopefully saw at least part of the transit, the solar eclipse that happened a few years ago again across the US, and perhaps you saw other solar eclipses around the world. So remember when the moon passed in front of the sun, the moon blocked out the sun's light and allowed you to observe the stars and the solar corona that normally are outshone by the rest of the solar disk. So if there's a way we can then put something in front of our star to block out the star's light, we can then resolve the light of the exoplanet. And that is exactly what the direct imaging method does. So what the direct imaging method does is uses something called a coronagraph. A coronagraph is like a fake moon that blocks out the light of that star and allows you to see the very small light of the exoplanet orbiting around that star. And we can totally do that actually today with technology. We can build something called a coronagraph named after the corona of the sun. And you can build a disk inside of an instrument that blocks out the light of that host star and allows us to resolve the light of the exoplanet orbiting around that host star. Can you all hear that, by the way?
Can we? Yeah, we can see this.
If there's
Can you hear it?
audio, we're not going to be able to hear it.
Okay, then I'll skip this. That's fine. So we're able to use a coronagraph, basically a disk within an instrument, to block out that host star's light and to resolve the light from the planets orbiting around that host star. So actually right here is some data taken from a large ground-based telescope observing a multi-planet system orbiting around a host star over about 7 years. So at the center, you'll see that black disk. That's actually the coronagraph blocking out the light from its host star right here. And you can notice these 4 little dots of light. These are actually the exoplanets orbiting around their host star. And as you observe this system over 7 years, you're actually observing a extrasolar solar system with 4 planets slowly orbiting around their host star. Okay, so now what? So we have discovered over 4,000 exoplanets. But now, how do we take the next step? How do we go from planet discovery now to planet characterization? It's great that there's an exoplanet there, but how do we determine, for example, what's in a planet's atmosphere? Does it even have an atmosphere? If so, what molecules are present in an exoplanet's atmosphere? Does it have CO? Does it have CO2? Does it have water? Does it have methane? Things that life needs in order to survive. And if so, could that atmosphere support life on its surface? And if so, does that planet actually have life on its surface? So now we move on to the next step. After we found an exoplanet, we have to determine if it can support life. So you might have heard of a lot of people talking about the habitable zone or the Goldilocks zone. So this is the zone where liquid water can exist on a planet's surface. And this is absolutely important because life as we know it in our own solar system requires liquid water to survive. So if we look down on the top of our solar system, there's the sun. Mercury and Venus are a little bit too close, they're a little bit too hot. Mars is a little bit too far away, a little bit too cold. But Earth is just in the right orbit, not too hot, not too cold, perfect temperature where liquid water can survive. And as we have liquid water on the Earth, we also have life. And that's why scientists were very excited when we discovered the TRAPPIST-1 system. This is a 7-planet system. These are all Earth-like planets, Earth-sized planets. And planets E, F, and G are all potentially in the habitable zone of their host star. So planets E, F, and G might have the conditions necessary for life to survive on their surface. So it's pretty incredible that we might have actually already discovered planets that have life on their surface today. But now, how do we go from planet discovery to saying, oh, the planet's there, the planet's in the right location, it could have life on its surface, to now actually looking at and peering into their atmosphere to figuring out what molecules are present in the atmosphere of these exoplanets. And this is a law that I actually use called Beer's law. So Beer's law is actually a physics law that allows us to, by simply studying light, to actually looking into the composition of the atmospheres of these exoplanets. So let's look at an actual textbook definition of Beer's law. This is studying for a test or doing homework while Beer is involved, making difficult classes such as physical chemistry more bearable. Okay, that's a good Beer's law. I did that a lot in grad school, but here's the real Beer's law. So what Beer's law does is it describes the absorption and scattering of light in and out of a beam. So let's say we have a light bulb right here, and we have a chamber of gas right here, like methane, carbon dioxide, or water. As I shine that flashlight or that light bulb through this chamber of gas, the resulting light will be a little bit dim because the gas will absorb light over various wavelengths. And depending on how that light is absorbed can be described here by this function. So in other words, if I know what the light should look like, and I know what the light does look like, I can then back out the composition of the material, the gas, the dust, that's causing that absorption and that scattering. So if I see a lot of absorption at 3.3 microns, I know that planet has methane in its atmosphere. If I see a lot of absorption at 4.5 microns, I know that an exoplanet has carbon dioxide or carbon monoxide in its atmosphere. So that's how we can actually figure out the molecules that are present in an exoplanet's atmosphere simply by observing how it absorbs, scatters, and emits light. So now let's pretend we're using our telescope and we're looking at a yellow sun-like star. Now that sun-like star, we would expect it to look yellow, right? Makes sense. But what happens if we put a giant cloud of gas or dust in between us and the star? Well, that gas cloud will absorb some of the star's light and cause it to look a little bit more red. So if we observe what the object does look like, and then compare it to what it should look like, it does look red, it should look yellow, we can then actually use Beer's law to then back out the composition of that gas cloud and imply or infer that that gas cloud has molecules in its atmosphere. Now let's take an exoplanet. Now, if we take a young exoplanet, these are planets that are relatively newborn. They have very hot cores, that's heat left over after they've collapsed together. And these hot cores emit a lot of light and heat. And then as they are emitted through the outer layers, the outer cooler layers of these exoplanets, that light is actually absorbed by the planet's atmosphere itself. So light that was emitted as yellow is eventually emitted outside the surface of the exoplanet as red. And then astronomers on the other end can use Beer's law and say, hey, that planet, for example, has
Is he
methane
frozen
in its
to you
atmosphere.
guys?
Oop,
Where's it?
question?
Oh, I thought your video is frozen and I didn't hear you for a bit.
Okay, still
Maybe it
good?
was yeah.
Cool. So now let's take Jupiter around our sun. The sun will emit some yellow light. It'll hit Jupiter's surface and reflect back red light because Jupiter has a bunch of different molecules in its atmosphere. And we can use Beer's law as an astronomer to infer that that planet has, for example, clouds on its surface. So Beer's law allows us to characterize an exoplanet's composition by observing how it emits, absorbs, and reflects light. So here's actually the spectra of a bunch of different exoplanets on the y-axis, and we've arranged them here in order of cold on the bottom and hot on the top. And on the x-axis are a bunch of different wavelengths of light. So we've taken that light and we spread it out into the rainbow of light that makes up that one signal. In these passbands, at these wavelengths, water absorption occurs. So if I see a bumper wiggle at these wavelengths, I can infer that that planet has water in its atmosphere. Now, this data were taken by a large 8-meter telescope from the ground. And at these wavelengths, that ground-based telescope, if it sees a bumper wiggle, it can infer that that planet has methane in its atmosphere. Also, at these wavelengths is where carbon monoxide. So if I see a bumper wiggle there, I can infer that that planet has carbon monoxide in its atmosphere. So some of you eagle-eye observers might have seen there's these lovely gaps in the data. So this is a ground-based telescope, and this is absolutely where the Earth gets in the way. So the Earth has lots of annoying things like water, like methane, like oxygen, and those molecules in the Earth's atmosphere absorb light and block out the light from stars and from exoplanets. So if I wanted to look at these wavelengths to observe these molecules, what do? Well, we can launch into space. And that's why the Hubble Space Telescope and other future space missions are so crucial. For example, Hubble has this instrument on board called the Wide Field Camera 3 or WFC3. And its wavelengths, the passband that it's typically used for is shown on the right blue. And these wavelengths that are probes happens to line up with water. So if you've heard a lot in the news that scientists have discovered water in an exoplanet's atmosphere, it's because we are limited by this instrument on Hubble. If we had other wavelengths available to us to observe these exoplanet atmospheres, we could then look into other molecules in these exoplanet atmospheres. So that's why we're very excited about the launch of the James Webb Space Telescope, because James Webb will have a lot more wavelength coverage. Not only will we be able to look at water, we'll be able to look at for other molecules like methane, like carbon dioxide, like carbon monoxide, and we'll be able to look for the molecules that we think that life needs to survive on the surface of a habitable exoplanet. And perhaps James Webb will allow us to start characterizing those planets that could potentially host life on their surface. A mission that I'm actually involved directly in at JPL is the Roman Space Telescope. So last week, this was formerly the WFIRST mission, and it was just renamed in honor of Nancy Grace Roman. She was the mother of the Hubble Space Telescope. And this is a Hubble-sized telescope, and it will study a lot of really cool different things. But one of the things that I'm most excited about the Roman Space Telescope is its capability to do direct imaging. And that's also because I work on this instrument. So I work on the CORONAGRAPH on the Roman Space Telescope. This is the instrument that allows us to directly block out the light from a host star to resolve the light from a planet orbiting around that star. So if we look at where we are today, we're mostly limited to large, bright planets. And these planets, since they're so hot still, they're typically very young. And they're also far away from their star. With the Roman Space Telescope, we'll be able to push in that boundary a little bit closer. So you can actually look at true Jupiter analogs. So Jupiter-sized planets, Jupiter-sized orbits around sun-like stars. And this stepping stone that the Roman Space Telescope gives us is absolutely crucial for making that final leap in technology to discovering and characterizing Earth-like planets orbiting around sun-like stars. So here we are today, looking at large, bright, hot, young planets. We want to get to small, cool planets, and the Roman Space Telescope with the CORONAGRAPH instrument will give us that stepping stone, that increment in technology to showing that we can do this from space and we have the precision necessary to look for Earth-like planets and to look for life around these planets. So space level is great stuff, right? You have the Hubble Space Telescope, we're going to have James Webb, we're going to have the Roman Space Telescope. Why even bother with the ground? Well, first off, there's only very limited in the number of, in terms of time and wavelength space given to us by space-based telescopes. So for example, there's really only Hubble that's able to characterize in detail the atmospheres of these exoplanets. Where on the other hand, ground-based telescopes, there's a ton of them, all with different telescope sizes and different instrumentation. However, you always have to be working against the Earth's atmosphere, which can induce large errors and large uncertainties in your data. So taking this in mind, we're actually commissioning right now an instrument at the Palomar Observatory. This is the 200-inch or 5-meter ground-based telescope at Palomar Observatory, just outside San Diego, California. This is at time, for about 50 years, the world's largest telescope. We're actually commissioning an instrument called the New Mexico Exoplanet Spectroscopic Survey Instrument, or NESSI. So right here is actually a picture of the NESSI instrument. No, that's a mythical sea creature. Sorry, guys. All right. Here is actually the NESSI instrument right here in blue. Here's some of its hardware. And NESSI is actually sitting at the very top of the telescope. So normally on a telescope, you have the light coming in, hitting the primary mirror, reflect to the secondary mirror, and at the bottom into its instrumentation. NESSI actually replaces the secondary mirror and sits at the top of the telescope. So in order to test and make sure that NESSI fits at the top of the telescope, we have to lift NESSI up from the ground floor over the primary mirror, this very historic, priceless, large mirror, and put it at the secondary mirror location. This is actually Michelle Creech-Ekman. She's a professor at New Mexico Tech. She's the principal investigator of this instrument. She's wearing a I Want to Believe NESSI shirt. Very, very appropriate for NESSI. And this is NESSI's first lift check. So NESSI is now being lifted off the ground and being lifted higher and higher and higher and higher above the telescope. We're hoping our insurance policy had started at this point. Luckily, everyone, it's okay. NESSI made it. Here's NESSI at the prime focus cage. Here's my boss, Mark. He's smiling. He's actually laughing at me because remember, I'm afraid of heights and I am the commissioning lead for NESSI. So I always have the privilege of going 100 feet in the air to deal with this instrument. It's horrendous. But despite that, I get some really cool photos. Here's NESSI at the top of the Palomar Observatory. And there's my feet. So it's kind of like a selfie. And we were actually able to just a few months ago observe the light from a transiting exoplanet. So NESSI is able to get really gorgeous data, and hopefully we'll be observing on it soon again. So that's how we find an exoplanet. We use those different methods. We use Beer's law to characterize the atmosphere of an exoplanet. We see if it's in the habitable zone. We see if it has water, methane, carbon dioxide, building blocks, things that are necessary for life to survive. The next step is we actually have to find the life that is on that planet's surface. Just because a planet could support life doesn't guarantee that life actually exists in that planet. So how do we find life? Well, let's launch a space telescope. And when it's going out into orbit or going out to the outer solar system, let's have it point back at the Earth and analyze the light reflected, absorbed, and emitted by the Earth. So we can look for evidence of oxygen, such as given by ozone produced by plants and algae. We could look for liquid water. We could also look for signs of things like cow farts, right? Things like biological activity like methane. But most importantly is we have to rule out all other explanations. We're finding water, we're finding methane, we're finding these molecules currently on exoplanets today. So you have to prove beyond a doubt that those molecules, those signals, those biosignatures that you're seeing in these planets' atmosphere is things from biology and not things that are occurring naturally. Another thing you can do is just talk to aliens, right? Voyager 1 and 2 launched in the 70s. They had this phonograph that was launched out, made by Carl Sagan and his team. So here's how you actually read out this phonograph. It was a bunch of greetings and messages from the Earth and pictures from the Earth as well. So here's how you read the phonograph. Here's how you turn those signals into pictures on your TV. And right here is the location of the Earth relative to a bunch of pulsars, so you can actually find where the signal came from. Similarly, in the mid-70s, SETI sent out a message from Arecibo to this very densely packed cluster of stars called M13, the Hercules globular cluster. Up at the top, this is actually the signal they sent out. So up the top is how to count. Here's molecules. This double helix is DNA. The red person is a person. This is the solar system, so the sun, Mercury, Venus, Earth elevated, because that's where the message came from. Mars, Jupiter, Saturn, Uranus, Neptune, and guys, this is the mid-70s when they didn't know any better. They included Pluto on the image. But of course, we know better, Pluto's on a planet. And then on the bottom in purple is Arecibo, the dish itself. So this message is saying, hey guys, we're humans, we're relatively smart, we know about numbers, we know about molecules, we know about DNA. Here's where we live, come and enslave us, right? Great. So another thing you can do is also send out social media messages because nothing bad happens on the internet, right? And this message was sent in 2008 to this planetary system called GLIESE 581, and planets C and D in the system are potentially in the habitable zone of this planet. So if life exists on this planet, these messages will arrive in 2029. And if aliens do live there and they're able to reply immediately, we'll be getting a return message in 2049. So the question is, where are we now today? Well, despite what the History Channel might tell you, unfortunately, we have yet to make any conclusive detection of extraterrestrial life. So I absolutely love Ancient Aliens. It's a super fun show, and my brother-in-law is obsessed with that. And he totally thinks that I know about the existence of aliens, and my clearance level is such that I cannot tell him. I can tell you guys right now, I believe in aliens. I think they exist, but I think we have yet to find them. They're out there somewhere. And I have lots of friends, for example, that work on Mars missions, on other NASA missions. We love, posting stuff to Facebook and Twitter and stuff like that. It's going to be very hard to keep that a secret if we do indeed find life. Because also, if I find aliens, I can make all that Neil deGrasse Tyson money, guys. I can just go on the lecture circuit and be super famous and be set for life. That'd be awesome. So the question is, why haven't we found any conclusive detection of extraterrestrial life? Well, maybe our technology isn't good enough. So for example, it took us until the mid-90s when we started making digital cameras, when we had CCDs and CMOS cameras that could have the precision necessary to detect planets around other stars. And maybe the signal is just so small that we don't have the precision yet to be able to observe it. Well, maybe we just haven't found them yet. Maybe we're looking over in this direction and aliens are talking to us in this direction. So Jill Tarter, she was the inspiration for the book and the movie Contact by Carl Sagan. She gave a great analogy for it. So let's say we take the entire universe and we shrink it down into the size of the Earth's oceans. So despite us thinking we know all these great things about the universe, we know about planets, we know about dark matter, there are still so many more things we have yet to explore, discover, and understand. And in that ocean of the universe, we have really only explored the equivalent of a cup of water. Or maybe, depressingly, maybe we are all alone. And personally, I think there's life out there. So again, we've had this awesome foundation that's been given to us by ground-based telescopes, and they continue to be to do interesting, cutting-edge, foundational, ground-breaking new science. The Hubble Space Telescope allows us to look at exoplanets, their spectra, to look for water. Spitzer, which I didn't talk about much tonight, but that allows us to also study the atmospheres of exoplanets. Kepler and TESS have discovered thousands and will discover tens thousands of more exoplanets. James Webb, when that launches, will be able to look at these exoplanetary atmospheres in exquisite detail. WFIRST, now the Roman Space Telescope, will be able to look at directly imaged exoplanets from space. And what's really exciting is thinking ahead to the next generation of missions that will be launching. So currently in astronomy, we're looking at 4 next generation missions. And 3 of those are LUVOIR, HABEX, and the Origin Space Telescope. And each of these 3 missions have been explicitly designed to detect life outside of our own solar system. And one of these 3 missions, if they're chosen, will be launching in the 2030s or 2040s. So perhaps in the next 10, 20, maybe 30 years, we'll finally be able to answer that question, are we alone in the universe? So thank you so much for your time, and I'm happy to take any questions.
Thank you, Robert. Eric, how are we doing on questions?
Yeah, there were some questions a little bit ago. If someone wanted to participate in the citizen science program, are there any limitations or restrictions on what size telescope or camera they could use?
Not at all. We're actually trying to figure out exactly what the bare minimum is. So if you're interested in joining, please go to our website, NASA Exoplanet Watch, get in touch, and we are happy to try to figure out exactly what's necessary to do that. Again, a small 6-inch telescope. I've done some estimates that maybe even a 3-inch telescope could actually do this as well.
Someone brought up Starlink. Do you have any thoughts about that? But I think it was answered online. I think Starlink's a problem with any of the exoplanet work?
Yeah, so it's mostly an issue of long exposures. Luckily, I don't need long exposures, so I'm very lucky that it hasn't impacted my science, but I know it has impacted many others.
I was going to ask you whether you're hiding any data about aliens, but I guess you've answered that.
Oh, I wish. I would make so much money just off the lecture circuit, so there's no need me to do that.
Jim Myers, are you finished, Eric?
Oh, go ahead. I'm still looking.
Okay, Jim Myers wanted to know if exoplanets have signatures. You know, you were talking about how they have gas. You can tell what gases they are and stuff like that. Do you recognize these planets by their signatures? Can you recognize planets by their signatures? Hello, Rob.
He's muted.
Yeah, check your mic. And by the way, we can turn on our cameras again because Rob has stopped sharing. Where'd you go, Rob?
Rob, you're muted. Your mic.
Down, pull your cursor down to the bottom of the screen, and you will find a place where you can unmute yourself.
Can you guys hear me?
There you go.
All right,
Also,
sorry.
although you're
Repeating.
I am.
we can hear ourselves through your speakers. Okay, go ahead.
All right, so
Rob,
you're asking about signatures of
about-
exoplanets?
I'm sorry, Rob, you were talking about spectroscopy. Is there any chance we can get the kind of spectroscopy we might get in the laboratory from a spectrometer from some of these space telescopes?
Yeah. So answering the first question, I think first is that so signatures around exoplanets. So unfortunately, I have memorized what water looks like around exoplanets. So I can look at the bumps and wiggles given to us by ground-based instruments, by space-based instruments like Hubble, and recognize water or methane or carbon dioxide. But you're asking, I think, specifically about what are the signatures that indicate that life exists around exoplanets. And this is actually a very much an outstanding question in our field about what are biosignatures? What are the bumps and wiggles in the spectra of exoplanets that indicate without a little bit of a doubt that life exists on the surface of these exoplanets? And that is absolutely an outstanding question today. And that's why a lot of people are spending a lot of time and research in labs, for example, on defining those biosignatures. So if you see a bump and wiggle at this wavelength, you can say, that planet definitively has life on its surface. Then the other question, can you repeat that one more time, please?
So can you get the kind of complex spectroscopy you might do on Earth, say from a visual UV or an infrared from some of the telescopes, or do they have that kind of instrumentation?
Yeah, of course. So right now I'm using an instrument at Palomar Observatory that is getting spectroscopy of exoplanets to look at their atmosphere. Typically, we're usually using larger instrumentation because it's able to get higher precision because these signals are so much smaller. But I would love to push the boundary and see how small of a telescope we can use. So if any of you are out there that have your own spectrograph and your own telescope, please get in contact with me. I would absolutely love to see how far we can push the envelope and see if we can actually start getting spectra from smaller ground-based telescopes of these exoplanets.
Is there you have any comment about double stars and how that might influence some of the planet observations? Because what was I reading that about half the stars are actually double stars?
Yeah, so half the stars you see in the sky are double stars. And we're actually finding exoplanets around some of these binary stars. So for example, Kepler 13b is a planet that's much like Tatooine in the sense that that one planet is orbiting around a binary star system. And so yeah, they do occur, which is pretty cool.
Alex, do you have any more questions? You're muted, Alex.
Sorry, I was distracted. There was the noise in my backyard. I did not know the Memorial Day weekend was a fireworks day, but apparently it is to somebody. Okay, I think we're wrapping up for tonight. And why am I? I'm echoing. Anyway, I want to thank Molly.
The echoing's coming from Tolga's computer.
I'm getting feedback from somebody. Okay.
Okay, okay now.
Molly was doing her thing as the director tonight, which gave Tolga a break, so Tolga was able to answer lots of questions. It's really good having a team of people doing this, and I really appreciate that. And of course, we're always indebted to our presenter. Rob, you had 50, 60 people watching you tonight, and in the course of the next week, you'll have 800 or so people seeing you. Folks, be sure to go down there and check the subscribe button so that you can take part in the Astro Imaging channel. We're here every Sunday night or Monday morning if you're in Australia or a lot of other parts of the world. And all these programs will go on our permanent record files here. So join us and come on back again next week when we're going to hear about how to process Comet Swan and PixInsight. So good night, everybody. Take it away, Molly.
Great job, Molly.
Yeah, thank you. Let's see if this outro works. I don't think